Hello, good afternoon, sir. Dear participants, good afternoon to all of you. Our experts has joined and we are starting very shortly. Good afternoon, sir. This is Afzal. Oh, hello. Hello. Good afternoon, sir.
Yeah. Good afternoon, Dr. Afzal. So, how your this conference is going on?
Yes, sir. It is going on very well. Short-term course.
Yeah.
How are you,
Okay.
sir?
It's a short-term course. Yeah. Right.
Yes, sir. How are you, sir?
So, yeah. Fine. And this is the TQ sponsored, no? Under.
Yes, sir. Yes, sir. TCube Third is sponsored.
Okay.
Yes, sir. So participants are joining. We will be starting very soon.
Sure. And the participant, how many total participants?
Sir, we have registered participants are near about 264. 250, right? Exactly.
Oh, very large.
So we have registration more than 250 and then we have restricted to 250 only.
Okay.
We have one of our coordinator, convener of this short-term course, Dr. Satya from NIT Jalandhar. Yes.
Yeah.
Good afternoon, sir.
Hello. Yeah.
Good afternoon, sir.
Good afternoon. Nice to meet
Sir,
you.
welcome
both of
you for our session, sir.
Yeah.
Thank you.
Good. So in the morning, actually, Professor Rajanna.
Rajana, sir. Yes, sir. So it was very interesting. So he gave in thin film sensors. So and he showed different sensors he has developed in his lab. So tactile sensors, impact sensors, pressure sensors.
Okay.
Yes, sir. And once I have come to IIT Kharagpur for attending this MEMS and microsystems workshop, 1 week workshop in 2013. I came, sir. IEEE sponsored workshop.
Okay.
So in that you had given one talk.
Okay. Yeah, these are some actually forums where we can meet and we can exchange our ideas, we can exchange our views, and showcase our different research activities. Not many.
Yes, sir.
You have any course on the microsystem? Any in your curriculum?
Yes, we have in our.
You are in the instrumentation.
Yes, sir. Instrumentation and control. We have in our program electives.
Acha, elective. Okay.
Yes, sir.
And so you have all the design softwares like console.
Oh no, sir. No, we there is no sensor design softwares. Like nobody has worked in MEMS till now. So I'm the first one who joined in 2018. So I just completed my PhD in 2017. So I joined here in 2018. So I have my work experience in smart structures and smart structure based sensors and actuators.
Gotcha.
So other people, they're working in sensor networks and sensor system design, not in MEMS.
Okay. So you have the design. So you will start your lab facility slowly. You will start.
Yes, sir. We are planning to start.
Yeah, basic in start with the basic things like console, software,
ANSYS.
or ANSYS.
Yes.
those will be very helpful. And then you can slowly you can start something in the hardware side also with different facilities in film deposition. Many things are now possible because today MEMS is not with a VLSI and very hi-fi lab facility.
Yeah.
You can do it in a different way. Different approaches are coming up, like paper-based, polymer-based sensor, flexible sensor,
Yes.
Disposable sensors with nanomaterials, a lot of things. If you go for the lab development, you can concentrate on the characterization facility rather than very high sophisticated processing equipment.
Yes,
You can
sir.
go for good characterization facilities. That actually will give you more depth of your device materials in any aspect.
Yes, sir. Yeah.
No.
Actually, during that workshop, we visited one of your labs where this micro pump, diaphragm-based pumps, and the centrifugal-based pumps. So we just explored. So it was quite interesting.
Some of my colleagues is also working. Professor Bhattacharya is also working.
Yes.
That's okay. This is so you have the instrumentation and control. This is a separate department.
Yes,
Or
sir.
it
Separate
is,
department.
you also have a electrical engineering. I think.
Yes, sir. That's separate department.
That is
Yes,
a
sir.
separate department.
Yes, sir. Yes.
Electronics. Do you have electronics department?
Yes, sir. We
also?
have electronics and communication. That
Achha.
is also separate department, and electrical is separate, and instrumentation and control is separate.
Yeah. But this year my son is now we are filling up the counseling form.
Yes, sir.
And I have seen your department also. Instrumentation is in the list.
Yeah, we have very few NITs are having instrumentation, and only NIT Trichy and NIT Jalandhar are having instrumentation and control. And NIT Silchar is having electronics and instrumentation. Sorry. And NIT Rourkela is having electronics and instrumentation under EC department.
Under EC department.
Yeah.
So yours is a old department.
Yes, sir. Yes, sir. We started in 1990s.
Oh, nice.
So yeah, it was there since it was as REC. Like this NIT was there as REC. So now, yeah. So from 2007, I think it has been converted into NIT.
NIT. Yeah. That's right. I came to know these things when I was filling up the counseling form for my son.
Yes, sir.
So let's see. So okay. So when just let me know when we start. I'm ready.
Yes, sir.
I'm ready.
Yes, sir. I think in 2-3 minutes we can start.
Okay. Sure.
I think we can start now, sir. I will just give a brief introduction about you, then you can start your presentations.
Okay.
A very good afternoon to all. Before the start of the session, I would like to give a brief introduction about our today's speaker, Professor Soman Das from IIT Kharagpur. Professor Soman Das received his MSc degree in 1988 and PhD degree in 1996 from Indian Institute of Technology, Kharagpur. He joined as assistant professor in School of Medical Science and Technology at IIT Kharagpur in 2007 and became professor in 2008. At present, he is also the head Advanced Technology Development Center, IIT Kharagpur. He was instrumental in setting up an state-of-the-art advanced interdisciplinary R&D lab in the area of biomems involving SMSD and ATDC, IIT Kharagpur, to promote MEMS and biosensor activity. So his group focuses on design, fabrication, and development of biomedical and microfluidic devices for efficient and economical detection of diseases for detailed understanding of chemical, physical, and structural information of cells in integrated fashion. In this endeavor, presently, the following activities are being pursued: development of MEMS-based flexible sensors, physiological characterization of cancer and normal cells based on electrical and mechanical properties in microfluidic platform, and paper-based low-cost sensor development. He has been actively involved in setting up the state-of-art advanced MEMS design and processing laboratory at IIT Kharagpur. He took leading role in development of several technologies like polymer-based flexible flow and pressure sensors for catheter integration, impedimetric sensor for biological cell characterization, silicon MEMS piezoresistive accelerometer for avionics applications, nano-engineered microthruster for satellite applications, quartz accelerometer for space applications. He has authored more than 120 research papers in reputed international journals and conference proceedings and obtained 2 patents. He is the regular reviewer of various journals like Sensors and Actuators A, Journal of Biochemica at Biophysica Acta, Journal of Micromechanics and Microengineering, Micro and Nano Letters, Nanotechnology, Measurement Science and Technology, IEEE Sensors, Scientific Reports, etc. He has been awarded DAAD Fellowship under Faculty Exchange Program and was also a visiting scientist at several universities in Italy and Australia. He is the principal investigator of several research and consultancy projects in the area of MEMS and microsystems funded by various government and private agencies. So we are really honored to have you in our session, sir. Now I request you to start the session, please, sir.
Okay, I hope I am audible to all of you.
Yes, sir.
Okay. Thank you, Dr. Satya.
Yes, sir. Thank you.
And I'm also thankful to Dr. Afzal and you for inviting me in your TQ workshop.
It's a pleasure, sir.
Okay. So it is now I'll start my presentation. I'll share my slides. Is it now visible? Slides?
Yes, sir. Yes, sir. It is visible.
It is visible. Okay. The pointer is also visible.
Yes, sir. But it is not in the presentation. Means it is not in the full screen mode. The slides.
But how to go to the full screen mode? I am in the full screen mode.
Sir, you can go to slideshow and you can go to slideshow, sir, please.
Yeah.
No, sir, in the PPT, or you can press Ctrl F5. Sir, please go to slideshow option, sir. Slideshow. So in the PPT, yes, sir. So then from current slide or from the beginning. Last, yes, sir, left corner. Yes, sir.
It is coming this way only.
Okay, sir. No problem, sir. It is visible. No problem.
Visible. Okay.
Yes, yes.
Okay, so good afternoon, you all.
Sir, good afternoon, sir. Hello? Hello?
I hope I am audible to all of you. So today I'll talk on the microsensors and actuators for the space application. So basically it is for a particular application I have chosen, and the entire work actually whatever I will talk about related to our lab work, that the sensors has been developed by my students, and along with my colleague, we have worked that one sensors and the one actuator I'll discuss. The specific application is, you can see here, the launching vehicle of our ISRO, that PSLV. And before going into the presentation, I'll just talk. This side you can see, this is a launching vehicle, PSLV. And the other side, I belongs to the medical science and technology. Okay. So there must be some link between these two. I am in the medical science, but I'll talk on this. Talking means it is we have worked on these sensors for the for development of the inertial sensors. Okay. And later on you will understand, yeah, although this is a very specific application, the sensors that we have developed, but definitely those sensors also have an application in the other domain. One of the major domain is your biomedical. Okay. Now coming to this this PSLV, this is the launching vehicle, and probably some of you have seen, or most of you have seen the photographs. This space vehicle is used to put a satellite at a Earth's orbit. The satellite is just kept inside this launching vehicle around this location, nearly top, and this entire length, you have a different your engines, and that produces the thrust, and the entire system will go to some location outside the Earth, and at a particular orbit, the satellite will be released, and it will be there in that orbit for nearly say 5 years, 10 years, 15 years. Okay, depending on what how it is designed, how many years it will give the service. Many things are involved. So it is a rocket engineering, and starting from the launching of the this vehicle and putting the satellite in exactly at that location in the orbit, and then for the next 15 years the whole satellite, entire satellite will move around the Earth. It can be a geostationary satellite for the agriculture, for the weather forecast, for communication purpose, or for the defense purpose. So there are several applications are there. Now you can imagine there are many sensors and actuators are present, not only in the launching vehicle but also in the satellite. There are two components here in the entire system. One is the launching vehicle. The other one is the satellite. Satellite is not visible here. You can see this is one satellite. Okay, and that is its solar cells and all are folded. Well, satellite is folded and then it is kept here. And then this is launch pad, and it will move up and goes out the orbit, the Earth's orbit, and then it will be released and the satellite will be there. And now you can understand that for a precise location, precise your launching, you need various sensors for real-time monitoring. Okay, satellite is there for the 10-15 years, but the longevity of this launching vehicle only 5 to 10 minutes, costing about 100 to 200 crores of rupees or more than that. Okay, this is the whole scenario of just a few points I am telling you. So you can understand, for the real-time monitoring and to put the satellite in the exact orbit, you have to monitor the launching vehicle in a real time, so that from the Earth surface. Okay, remotely we have to communicate. and we have to control it through feedback mechanism, so that yes, at that particular orbit the satellite will be released and it will be there. Then for the 10-15 years it will rotate, but don't think that it will be there for 10-15 years it will be there in the same location, same orbit. Because of the several factors, interaction of the solar systems, electromagnetic wave, all together, the satellite may shift from its actual position, actual orbit. And if it's a shift, then I lost my communication. Many of the times we have seen it in while saying the TV signal is not there, satellite is not in its position. So you need a very precise location. For that you need a sensors, you need actuators also. Okay. For sensors, you have a temperature sensor, pressure, flow, many sensors are there. Today, I'll talk about only one sensor, that is the accelerometer. And this accelerometer will measure, accelerometer means it will measure the acceleration. And acceleration means we can understand that the class 10th knowledge, F is equal to m into A. So that A, if I can calculate that A for this launching vehicle, and in a real time when the launching vehicle has fired and it is in the projectile motion for only for 10-15 minutes time, then after that it will just lost it, because after releasing the satellite it will lost, entire vehicle will be lost. Okay, for the 10-15 minutes it will be monitored from the earth surface. And there today I'll only talk about the accelerometer. That means I want to locate in real time x, y, z coordinate of this launching vehicle in real time. Positioning sensor that I can extract from the acceleration, F equals to ma. If I know the A, I can get the V, and if I know the V, then I can get the A coordinate. And for the 3 axes, it is the 3 acceleration I have to measure, AX, AY, AZ. That means 3 accelerometers should be there. Okay. So I'll talk on that, and I'll also talk on, as I told you, the satellite as it is moving around the surface at a particular orbit, but because of the different interaction with the solar system and electromagnetic wave, it may shift. So you have to keep it back again from the remote control, okay, from the earth surface. And there a satellite, it's a very big, 100 kg, 50 kg, 10 kg. You have to bring it back remotely, so you need a thrust. We call it it is thrust we call. With that force, although it is a force basically, but as it is a very instantaneous, so we call it a thrust. With that thrust, it will bring back to its original position, original orbit, remotely. So this is a actuator. I'll also talk upon this actuator. Okay. So this is my outline. Sensors, different types of accelerometer. I'll talk on our development project of a project, that is the silicon MEMS piezoresistive accelerometer, and then I'll talk on the microthruster, which is actuator for repositioning of the satellite, and this vaporizing liquid microthruster that we have developed. Both the things we have developed, the accelerometer and microthruster, under with collaboration with the ISRO, okay, under the project mode. And for this, developing these two, many students have worked for their PhD, particularly for their PhD work. I got the 2 MS thesis also out of this accelerometer and thruster. But several PhD students have got their degree on these 2 projects. Okay. Here, the satellite, just giving you some overview. In the past, you have a satellite which rotates in the Earth, around the Earth orbits like this, it was about the 1000 kg, 20 years back. Then the people have thought that instead of going to the very large or heavy satellite, I'll bring down the weight of the satellite. And presently you can have a about 20 kg satellite. Okay, you have a different your mass, large satellite, small, mini, etc. Pico satellite, it will go below the 1 kg, and accordingly the cost will also reduced. Because of the cost reduction, people are moving to the smaller satellite. In the large satellite, you can have many applications. One satellite can work for the many applications: weather forecasting, agriculture, communication. But later on, scientists thought, let us now have a smaller satellite, and individual satellite work for a specific application. Because one factor is that if you see that if the satellite is large, having some 3-4 application, its cost is very huge, and if it fails, the entire the funding will go. You will not get any revenue, because our Indian country, this satellite is very matured, and we are getting lot of revenue of using this satellite. Okay, so if it fails, there is a cost is involved. So people thought, if I have a smaller satellite, then the cost will be less, and if it fails, then there is not much burden in our economy. That way, people are going to the micro satellite or nano satellite. Okay. Now coming to the sensor part, inertial sensors. So most important type of mechanical sensors I'll talk. You have a different sensors. The inertial sensors, you have a two most important one. That one is the accelerometer, micro accelerometer, that actually measures the acceleration or velocity or position. And another one is a gyroscope or gyrometer, which actually measure the rotation of any system. Okay. I'll talk only on the accelerometer side, but both are there in your launching vehicle, in your satellite. Both are sensors are there. Okay. The micro accelerometers have a different applications. Although I'll talk only about the specific space application, but here you can have an automotive application, because most of the today's four-wheeler have their airbag system for the safety purpose. This airbag, it will deploy, for deployment of the airbag, you should have my accelerometer. That sense, what is the acceleration? Any accident means there is a sudden jerking. That means there is a certain acceleration, huge acceleration at a certain moment.
Excuse me,
that
sir?
acceleration I gave, it is a 50g. You can understand, g is the acceleration due to gravity. If it is a 50 times of that at a certain moment, and that happens in most of the accident,
Excuse me, sir?
automobile accident.
Excuse
So
me,
take
sir?
it that the 50g. So if I have a accelerometer sensor which can sense the 50g, then the airbag will be deployed.
Hello, excuse me, sir. Sorry to disturb you. I think your slides are not changing, sir.
I am not getting the sound. Okay, I'll put my, just 1 minute.
Yes, sir. Your headphone.
Yeah.
Sorry to disturb you, sir, but your slides are not changing.
I am now in the 5th slide.
Sir, yes, your slides are not changing. We are on the first slide only.
Oh,
I think
how it is?
all the participants are facing the same problem, sir.
Shall I quit and upload again?
Yes, sir. You can try.
Sir, instead of sharing your entire screen, you can click on the option a window, so you can share your presentation. Yes, so I think that would work.
Is it moving now or not?
No, sir.
No. Then what happened? Is that slides there is available to you? I mean,
Yes, sir, slides are visible, but it is in the first slide only. It is not moving.
Is it now? Is it moving?
Yes, sir.
Yes,
It is.
sir.
Yeah, it's moving, sir.
But it is not in the slideshow mode.
Okay, that's okay, sir. No issue.
Okay, sir. No problem.
Okay. Sorry, I could not get it because I have some problem with my speaker also. That's why I kept it outside. So anyway, I
sir.
hope these things are now. Where I'll get my pointer? Here I'll not get my pointer. I'll move my cursor. You can see my cursor movement.
Yes, sir. Yes, sir. We
Okay,
can see.
So the inertial sensors I was talking about. So mostly the inertial sensors are the two parts. One is the accelerometer, another is the gyrometer. Accelerometer actually measures the acceleration of a system, moving system, and from that you can get the velocity, you can get the position also. Whereas the gyrometer actually, or gyroscopes, it measures the rate of angle of rotation. So any system that rotates, then to measure the rotation, you have to put a gyrometer. So any missile, when it is launched, it has a projectile motion. Along with that, it also rotates. So they are actually also need a gyrometer. And for the satellite, when it is moving, there also you need to measure the rotation speed. But today I'll only talk about the accelerometer. So now coming to these accelerometer applications, there is a different application. First one is the automotive application, where it is the airbag. In most of the current your up-to-date four-wheeler, you have a airbag. Airbag is deployed for the safety purpose. When airbag will deploy, that means when there is an accident. The accident means there is a certain, very certain acceleration, and that acceleration I am denoting it as a 50g. 50g. G is the acceleration due to gravity, and it is a 50 times of that. Otherwise, when a vehicle have a velocity or acceleration, in most of the cases, it is going up to maximum up to 4g. If it is for a very high speed, when you are getting the very high velocity. But when there is a acceleration or deceleration, in the accident mode, it goes to the 50g to 100g. That is for the accident. So the airbag, it is connected with a sensor, accelerometer sensor, and that accelerometer will only sense when there is a 50g. Otherwise, when this vehicle, four-wheeler, it is moving, always it has acceleration. But due to that acceleration, the airbag will not deploy. It will only deploy if the sensor will sense the 50g only. For the normal, the acceleration and the velocity, you will have another sensor, accelerometer sensor. And there the specification for that acceleration will be different. But in this case, for the airbag, it is 50g or 100g. Similarly, we have automotive braking system, suspension system to implement vehicle stability. Vehicle stability when it is moving. Okay, and there you should have the accelerometer. Then you have a consumer applications for a stabilization of the active stabilization of the picture in the camcorder. That means when a video is taking place, there must be something which is have some acceleration. And to get the stabilization, to get a very good quality of picture, video picture, then you have to put an accelerometer. Similarly, you have many things: three-dimensional mouse, sports equipment. For the biological activation, For the activity monitoring, you need a accelerometer. In the industrial applications, okay, avionics application, military application, of course, in different missiles. Okay, when the missile is launched, in the real time, it will monitor what is the position and the rotation. And then from the control room through feedback mechanism, you can control the missile, and that's why it is a guided missile. And so that 1,000 kilometer apart, it will target, the missile will target exactly at 1 meter by 1 meter. That is the precision we can achieve. All these are possible if you have a sensors. Okay. Seismometry, microgravity measurement, so various applications are there. So when I am talking about the 50G for the airbag deployment, when I talk about the satellite, it will also have a 10G. 10G. Okay, G you can understand, this is the acceleration due to gravity and 50 times of that. But when I talk about the microgravity, that means when that a lunar vehicle it will launch on the moon, and there the G is very less. But still I have to measure that the acceleration. Therefore I require a micro G accelerometer. See, for a application, specific application, you need the different ranges also. Sometimes 50G, sometimes 100G, sometimes micro G. For consumer application, it is 5G. For seismography, it is a different G. It is not 50G. It is very, very less. Now, when you will design the sensor, I should know what are the specifications you need. Accordingly, I'll choose my devices. Coming to the mechanical model of the accelerometer, just I have shown it here. So if it is a capacitive sensor, it is a, you have, for an accelerometer, you have a proof mass. Proof mass means it is a heavy mass compared to the other component of the device. So I can take this is as a heavy mass. And this mass is suspended through a cantilever. So if I take a mechanical equivalent of the accelerometer, you have a heavy mass, and it is connected with a fixed system. That means you have a spring. Okay, and here through this cantilever, it is connected to a fixed beam. Mass is suspended, but it is connected to the system. So the system it is moving, and I have to measure the acceleration of this system. So the accelerometer, where I will put it there, the proof mass is suspended there, but by some mechanism that proof mass is connected to this system. Okay, so when it will move, it will give some forces. It will generate the forces to the proof mass, and because of the heavy mass, M is very large, a force will be acting on this whole system, and because of this force, I'll get that acceleration. Okay, and in the mechanical equivalent circuit, if I take this is a cantilever, if it is a cantilever, then it will have a spring. So the mechanical equivalent of a cantilever is a spring. K is the spring constant. Also in this system, it is a mechanical system, so it has a damping effect. Where damping means whether the whole mass is moving under vacuum or at a atmospheric pressure, or it is at a higher pressure. Depending on that, it will give some damping effect. So this is the damping effect. Okay, so this is altogether, it is a mechanical equivalent of an accelerometer. So here I have talked about the principle. External acceleration displaces the support frame related to the proof mass. So this is the support frame. This support frame, it will move when there is acceleration. So as it moves, so there is a relative position to the with the proof mass, okay, which in turn changes the inertial stress in the suspending spring. So it is a cantilever. Here you have a proof mass, heavy mass is suspended at the free end. Now this is fixed to the system. This is moving in the upward direction. There is acceleration. But because of the free end and heavy mass, it is at the inertia, it will not move, it will bend. So it will bend because it has moved, but this will not move because of the inertia. And therefore a stress is generated. A inertial stress is generated in a suspended spring. Okay. And there is a relative displacement between the frame and the proof mass. And now this relative displacement you have to measure it. Okay. By different mechanism. Okay. Before going to that, what are the different mechanisms? I just given you one slide where you can just see for a automotive application and for the navigation, defense application, space application, what are the ranges? Typical range. Range is 50G plus minus or 2G, vehicle stability for airbag. For the navigation, it is plus minus 20G, but this is only the typical value. This data may change also. Resolution, it is 100 milli-G should be the resolution, but in this case 4 micro-G because it is for the space application or the defense application. Frequency range, it will work within this range. It will work lower frequency. Temperature range, most of the defense and the navigation system will work for the up to 125 degrees centigrade. For commercial application, you can go 70-80 is sufficient. Off-axis sensitivity. Off-axis sensitivity means the acceleration is a vector quantity. So when I talk about the acceleration, it is AX, AY, Z. So if a system, mechanical system, it deflects in the Z direction, it deflects, but it will also have some motion in the X and Y plane. And because of that, it will generate some your output at the sensor. But it is not the actual output. Actual output is only because of the Z axis. But because of the mechanical design of your system, it will sense for the other two axes also. These axes, the acceleration or output of that two components should be minimized, and that is known as a off-axis sensitivity, which should be less than 5% for the commercial application, and it should be 100 times less or 2 orders less in the defense or navigation application. And there is a TC temperature coefficients of sensitivity or non-linearity. Move forward, there are different transaction mechanisms. One is the piezoresistive mechanism, then the capacitive, tunneling, resonance, optical. Piezoresistive pickup, that means the piezoresistant, you must understand, silicon being a semiconductor, it is a piezoresistive material. That means if I apply a force or pressure, the resistivity will change. That is a piezoresistive material. Silicon is a very good piezoresistive material. And I will utilize that property for making a accelerometer. Then you have a capacitive accelerometer. Capacitive accelerometer means the capacitance will changes. And then you have a tunneling accelerometer, tunneling current pickup. This is one kind of a transaction mechanism to get microgravity, to measure the microgravity, micro G, 10 to the power minus 6 G. In that case, that piezoresistive or capacitive sensors will not work. You have to go to the different mechanism. Okay, that's why you have this resonant frequency. Also, you have resonant. You can understand for any mechanical structure, it will vibrate at its resonant frequency. Vibration will be maximum. Energy dissipation will be coupling will be maximum at the resonant frequency. Based on that, I can make a accelerometer. I can make a sensor. Okay, and those sensors are available. And other than that, you have optical and piezoelectric sensors also. There are several technologies used for making this type of sensors. One is the bulk, surface micromachining, electroplating, and this process. Coming to the piezoresistive sensor, just giving you an outline of that. It is your cross-sectional view I have shown you. Here, this is a cantilever. This is a cantilever, and at the free end of the cantilever, you have a proof mass. The other end of the cantilever is fixed to the system, or that this system is moving. This whole system is moving, okay? And I want to measure the acceleration of this system. And I have kept this accelerometer, which is connected through this cantilever to their frame, okay? And a heavy mass is suspended at the free end of the cantilever, okay? And this structure have some advantages, and there are several advantages and disadvantages are there. Now, what will happen if there is a acceleration or there is a deceleration? That means the whole this system is moving in an upward direction in the z-axis. So entire system will move, but as this is in a suspended condition, proof mass in a suspended condition, it will not get that inertia, so it will try to remain in its original position. But this has moved up. So there is a bending of the cantilever. Bending of the cantilever will happen, and because of this bending of cantilever, a stress will be developed at the fixed end. Stress of the silicon material will be developed at this fixed end, around this corner. And the stress is proportional to the bending or how much displacement is, or eventually it is what is the acceleration, okay? Now, under the maximum stress region, if I put a resistance, which resistance value will changes because of this stress, and measure the delta R, this delta R will be proportional to the force or the acceleration of the whole system. Okay, so this is the piezoresistive accelerometer. So the entire cantilever is made of a silicon, and at this junction I'll put a resistance, and at this junction I'll put a heavy mass. So when there is acceleration, this will bend either in a downward direction or upward direction, depending on which direction the acceleration or forces is acting. And then as the cantilever bends, so there will be a stress and developed, and the stress, because of this stress, the resistance, the implanted resistance value will changes. There is a delta R is there, and if I can measure the delta R, which is proportional to the force acting or the acceleration of the system. Okay, this is the whole idea about this piezoresistive accelerometer. One of the most disadvantages is the large temperature sensitivity. Piezoresistive property, it is very much dependent on the temperature, because the students who are in the electronics physics, that you know that the energy band diagram, free electrons in the conduction band, and because of the temperature variation, there will be a change of concentration in the conduction band, and therefore the changes in the piezoresistance will occur. Therefore, piezoresistive sensors are quite sensitive to the temperature, which is a disadvantage, and you should have a temperature compensation circuit for that. Coming to the capacitive accelerometer, in the capacitive accelerometer, how it follows? Just like the principle, just like this principle, mass and spring. Okay, so here in the piezoresistive accelerometer, you have a mass and a spring. Similarly, here also I have a mass and a spring. A heavy mass, it is connected to the frame by using the two cantilevers. Instead of one cantilever, I have used the two cantilever. And at the proof mass, this end you have made a two electrode, which will act as a capacitor, and the bottom also you have a two capacitor. Two electrodes are there. So you have a two capacitor. One is at the top, another is at the bottom. And now, if the whole system moves, this proof mass is suspending. And if there is an acceleration, I mean along the z-axis, if there is an acceleration, then the proof mass will move in either upward direction or downward direction. So the gap in one capacitance will decrease, another one will increase, and you will get a delta C value. If I can monitor the delta C, I can get what is the acceleration. Okay. This is the whole idea of your capacitive accelerometer, and it is a very sensitive, and you require a very low power consumption. But there is a disadvantage: is the electromagnetic interference is there. Okay, and parasitic component you have to remove it. As a very details of the piezoresistive, I'll now talk about that project we have did it successfully with the ISRO. And before going to that, the capacitive accelerometer, just giving you some example how this capacitor I can make it. Okay, here you can see this is a comb-like structure. Although this is not our work, I have just taken it from the literature only. People have worked around the globe. So here one type of capacitor, capacitive accelerometer. You can see here, this is the design. The entire this is red colored. It is a comb-like structure and it is suspended. Suspended, but it is anchored at this 4 point. At this 4 point, this is the anchor. This is the actual figure of your image of your devices. And here, this is the anchoring position to the substrate. Otherwise, the structure is suspended. You can see there is a gap between the substrate and the cantilever. There is a gap. And these are the comb structure. You can see the enlarged view and the magnified view. Okay. So, because of the presence of this cantilever, and there is a mass. This is the heavy mass. You can see. Okay. And the green one, they are also the fixed electrode. They are fixed plates or fixed electrode. Now I can get that this, it is a comb-like structure, and here each pair will form a capacitance, red and green. This is one capacitance, this is one capacitance, like that, and they are in parallel. All capacitors are in parallel. And now there is the acceleration, and this acceleration is in plane acceleration. In the other cases, it was out of plane acceleration. Now I am giving an in plane acceleration, either in this direction or that or other direction. So the comb, they will move to the nearer or goes apart. What will happen? The capacitance C equals to epsilon A by D. D value is changing. D value is changing, so the capacitance value will changes. The equivalent capacitance, if you monitor, you will get a changes, and depending on what is the acceleration, and it is the you have they are proportional to each other. Okay, this is one way. I can make it another design also. In this case, the mass is moving in this direction. That's why I am taking the D value gap between the capacitor electrode. But now coming to the other way. If I have designed in such a way that the mass, it is moving in this direction. Okay, it is sensitive in this direction. By designing this cantilever in a different way, then what will happen? As these are moving in this direction, so there is a change of area, not the D value. It is now the change of overlapping electrode area. That also it will affect your equivalent capacitance. So both way it is possible, and people have worked, and commercially available chips are also are there in the market. Okay. Now I'll talk about the design and development of a silicon piezoresistive accelerometer using the MEMS technology. Here basically whatever I did, it is your silicon piezoresistive accelerometer. I have shown you the cross-sectional view. You have and this is the top view. You have a proof mass, and this proof mass is suspended by this four cantilever, 4 beam, very thin beam. Here you can see the cross-sectional view. Okay, and whole system is connected. This is the sensor. Whole system is connected to your bottom plate and the top plate covered with by packaging process. So and it is connected to your entire system, for which I want to measure the acceleration. It can be launching vehicle, it can be satellite. When there is acceleration, the system will move, but this group mass will not move. Because of the inertia, it will not be in phase with the frame. So it will bend. Because of the presence of this cantilever, it will bend like this. Okay, it will bend like this. And here, instead of having a 1 cantilever, I have put a 4 cantilever to make a mechanically stable system. If it is a 1, then not only this, but if it is having a force in this or in the other direction also, there will be a torsional bending or the rotational bending is there. To avoid all this, because of that, there will be off-axis sensitivity. I want to measure the z-axis only in this direction, not in other direction. But the design, mechanical design is such that the other axis it also senses. So I have to make a rigid structure in a other axis. And for that case, instead of only 1 beam, I have put the 4 beams so that it will be rigid compared to the previous one. So here, this is the whole concept. With this concept, we have designed it. And you can see in a console we have designed, and I have put, if I give a force over here, there is a bending of the beam, and there is a stress is developed. The colored red region or green region, you can see there is a maximum stress, tensile stress, and the compressive stress, where I'll put a resistance, because the entire chip is made of silicon, and I have put a piezo resistor only at the maximum stress region. Okay, and so altogether you have 8 resistances. In each beam you have 2. One is a compressive, another is tensile. And then you have 4 beams, so you have altogether 8 beams, piezo resistors are there. And if you have 8 piezo resistors, you can make a Wheatstone bridge circuit to get the output of that. Okay. Now, as there is a bending, so stress is developed at each corner of the cantilever. And there you have the stress, the piezo resistors, so that there will be a change of delta R in the Wheatstone bridge. Okay, and if I can measure the change delta R, I can get what is the force acting over there, or it is the acceleration. What is the acceleration acting on this sensor surface? This is the whole idea. Details are there, and now come to the other one. What I told in the previous case. My force direction is perpendicular to the proof mass, always. That's why it is called the single axis accelerometer. When I talk about this one, it is a cross axis. Because of the mechanical design, I have chosen the 4 beam to get a more stability, but still it is not a completely fixed in this x and y axis. If there is a force, in the along this direction, it will bend in this way. So there will be a stress, and if a stress is developed, you will get some Wheatstone bridge output. That Wheatstone bridge output, although it is low, but it is not ideally 0. There is some practical value. The sensitivity, calculated sensitivity is about 0.943 ppm per G. That is 1.15% of Z-axis sensitivity. Okay, so it is not 0. I have to make it a 0. And that is the challenge of your mechanical design. Similarly, if you have a y-axis in this direction, in plane acceleration of force is there will be a torsional force is acting. It will rotate, whole structure will rotate, and as it rotates, the cantilever will have a stress will be developed. And if the stress is there, in the Wheatstone bridge, you will get some output. And that output is coming because of this motion, not because of the z-axis forces. Okay, so I have to make a mechanical design such that this off-axis sensitivity should be minimum or less than 1%. Less than 1%. So far you have a 1% or more than that. I have to make it less than 1% even for the commercially viable sensors which are used in the airbag. I am not talking here about the aerospace. If it is a space application, it should go to the 3 order less. Okay, so this is the challenging task. After giving you some of the design aspect, here you have to fabricate it. Once the design is over, you can make the layout of the whole structure for the processing, and this is the entire process for starting with the N-type wafer, then go for the oxidation, then you do the lithography and make a window to make the resistances, at the different locations, and you dope it with a boron or phosphorus. After doing all this, again go for the lithography and take the contact, and then you do the bulk micromachining process by which you can make the cantilever, which is very thin. So these are the entire process, although it comprises the 9 steps, quite complicated, but by using all this process, finally you will get the wafer, you will get the sensors. And here you can see some of the sensors wafer level. Okay, in one wafer I can make a 12 sensors array, and here you have the single sensors. This is the proof mass, and here you have 4 cantilevers, and in each cantilever you have those piezo resistors, and they are connected in a Wheatstone bridge form. Okay, these are the interconnecting lines, and here you have 4 bond pads at the periphery, which will get access to the Wheatstone bridge. Okay, and once you did it, then you have to cover it, package it, and this is after packaging. Once you package, then you can go for the measurement. And here just one output I have shown, one on characteristics I have shown you with the applied G, say plus minus 5G. These sensors was designed for plus minus 5G, and the accelerometer output, the Wheatstone bridge output is quite stable and linear also, up to 5G. Okay, it is quite okay, and we have achieved that. But if you see the Z-axis sensitivity, for the Wheatstone bridge output, it is 570 microvolt per G. Whereas for the X-axis, it is 3.5 microvolt per G, and this is 4 microvolt per G. That means it is nearly 1% or more than that. Although I have achieved the sensitivity for the Z-axis, Z-axis means perpendicular to this plane, and this is the prime axis we call. But for the off-axis, it is still more than 1%, which is not a good design. Okay. And you have some linearity. So far, we have a very good linearity from minus 5G to plus 5G. Okay. Now, later on, we have changed our design of the accelerometer to get same sensitivity, because sensitivity I have achieved for the Z-axis, for prime axis, whereas the sensitivity of the off-axis is quite large. I have to suppress it. While after first phase of iteration, we understand that there is a problem in the mechanical design. Because of that problem, you are getting very high sensitivity in the X and Y. What is that problem? Although sensor will work in the electrical domain, but we have to understand what is the mechanical design. So it is a interdisciplinary. MEMS is a sensors it is a interdisciplinary nature. You have to have a knowledge in the different domain, physics, chemistry, making the device itself get a knowledge of the material science, make the knowledge of the chemistry. Making the sensor parts, you need the electrical engineering, electronics, but of course you also need the mechanical engineering knowledge also. So it is a combination of all, and it is an interdisciplinary subject. Now if you see carefully, the displacement along the Z-axis, the formula is used as this one. Okay. Now if you carefully see, this is the cross-sectional view, this is the proof mass. For the proof mass, as the thickness is very large, 300 micron, 300 micron is your thickness. The center of gravity is here. Center of gravity is at the middle of the thickness direction. But what about the cantilever? Cantilever, I told it is a very thin compared to proof mass. The thickness of the cantilever only 10 micron. And its CG is here. CG is here only. Whereas for this case, CG is here. So there is they are not in same plane. They are here, but it is here. Because of this not linear, not in one plane, the whole system, if you give a force, in plane force, there will be, of course, there will be a rotational movement. And that you have achieved while you design for the off-axis. Because of the change of CG, you are getting these changes. And for that reason only, as a result, you are getting the off-axis voltage at the piston bridge. Okay. That means it is not very much stiff in these two X and Y axis. I have to make it a stiff. What is needed? I have to make this center of gravity for the cantilever and the proof mass in the same plane. How it is possible? Here, if you carefully see, you can see that this is a same plane. Okay. Now, only in the proof mass, around the proof mass area, on the top of that, I have put another mass. So now the total thickness is this much, and the center of gravity, instead of here, it will move here. So it is nearer to this center of gravity. They are in the same line. By adding some extra mass on the proof mass, you can change the center of gravity and bring it near to the in the same plane of your other your cantilever. Okay, and with that you can achieve the rotation, torsional rotation. It will be reduced, and you will get the higher off-axis sensitivity. Okay, that we did it. What actually we just put after making the entire devices, I put some extra mass made of gold material on top of that. Okay, and with this extra mass, you can see some of the things. Yes, here these are the extra mass that we have put it, gold, and by that way, when you measure the off-axis sensitivity, it is reduced much reduction is there. Okay, with structure and without structure, this is for the z-axis and this is for the x and y-axis. You will get a much reduction in the off-axis sensitivity. And if I compare it, you will see that the sensitivity in the x-axis is this 0.1 millivolt per G, but for the x and y-axis, it is 0.5 microvolt. 0.5 microvolt per voltage per G. So by changing or modifying your design, mechanical design, you can achieve this also. Okay. So with this, I will completed my lecture on the accelerometer. And if you have some more time, just 10 minutes I'll take. I hope it is available. Observe.
Yes, sir. Yes, sir.
Okay.
You can continue.
Okay. So now I'll talk about the actuator.
Continue.
Okay. Thank you. I can now I'll talk about the actuator. As I told, a satellite, when it is placed around the orbit, the satellite is placed. Okay. But because of the various reasons, the satellite may shift. A drift is there. So I have to bring it back to this orbit. Otherwise, I will lose my signal. What way I will bring it? Because I have whatever I will do it remotely. And this is the satellite. You can see just a pictorial view I have shown you. satellite, as I have told, it is a several kgs is there, 100 kg to 2 kg, and I have to bring it back to its exact location remotely. And you need something which is known as a actuator. By using that actuator, we can control or we can reposition the satellite. There are many different types of thrusters. So basically, it is a thruster call, and it is a micro thruster. Why I call the micro thruster? Not I. In general, it is called. That you will understand in the next slide itself. There are various types of the thruster is there. Ion thruster, Hall effect thruster, etc. Cold gas. I'll talk only about the vaporizing liquid microthruster, VLM, vaporizing liquid microthruster. Okay. With that thruster as an actuator, I can bring back a 100 kg satellite to its original position remotely. Okay, let us see, move forward. In this slide, I'll just talk about very briefly what do you mean by the microthruster. Actually, this whole concept was first generated by the, practically bring it by a jet propulsion laboratory of the NASA in USA. Okay, probably in 1998. Okay, the very simple concept, and that of course whole countrywide we do in our Diwali. Think about that. I have shown you the 3 layers of material. Let us take it as a silicon, or you can take it as a glass. Three different glass slides. It's a simple glass slides. In the bottom glass slides, you have put 4 resistances, thin film resistance. These are the 4 thin film resistance I can individually access. In the middle slides, you have made it through holes. The glass slides, you have made it through holes, and the diameter is very, very small, 1 millimeter or 500 micron or 100 micron, but it is a through hole. In the top slide, you have a diaphragm. These are the 4 individual diaphragm. Diaphragm means it's a very thin layer. Okay, the entire glass substrate is very thick, but the diaphragm is very thin. Okay. Once you make this individual layer complete, then you bond all together in an aligned way and bond together. Aligned way means this resistor will be aligned with these holes with this diaphragm. So you have a 2 by 2 array. While you are bonding and bringing all the layers together, in the through hole position, I'll keep some of your material, powder, which actually ignites or get ignited at a very low temperature. Those materials are available. Okay. And the amount requirement is also very, very small. Only few microgram or nanogram is sufficient for that in a powder form. And whole thing can be packaged here. So it is the NASA lab, Jet Propulsion Laboratory is the first digital microfluidics, digital microthruster. So once I need the satellite has gone out of the orbit, I have to bring it back. I have to give it thrust. Remotely, one resistor will be switched on by electronic means. They have the feedback mechanism. Feedback mechanism means the satellite has gone to the different position, X, Y, Z. There are also some accelerometer is there. That will get the position, and it will send the data to the ground control room. They will sense, yes, I have to give a thrust. And they will calculate how much deviation is there, at which angle, everything very accurately, remotely, they will do it. and then they will put, yes, this much amount of thrust is needed to put the satellite back. One resistor will be fed through feedback mechanism. As it fed, fed means the current will flow through that. At current is flow, it is a metal thin film resistors. Temperature will increase. As the temperature increases, the materials which are there, it has a very low boiling point. So it will fire. It will simply fire. Just like what we do in the Diwali, the rocket, you ignite, it will go up. And that means you are igniting your material, and what happens, as they are in a closed form, they will generate huge amount of pressure. The pressure that is sufficient to burst my diaphragm. And it will burst out, entire force will go up in the upward direction, and the satellite will move in another direction. This is the whole concept of a thruster, micro thruster. And this is the digital thruster. First, it was conceptualized, designed and fabricated, realized by Jet Propulsion Laboratory, NASA. And you can understand why we call it as a digital, because one thruster will be used for one time. Once it is gone, used, it is over. For the next, you have to ignite the other resistance and go for the another one. Then next one, this way. That's why it is a digital thruster. I can use this concept and go for some other mode, which is a analog thruster. Whenever I require, I'll flow some fluid, give the thrust, and whenever I do not require, I'll stop my fluid flow and thrust will be stopped. That is the whole concept. So let us move forward here. I can show you. Before explaining the structure, here it is a target specification. Weight of the satellite is 10 kg, suppose. Because we have designed for that. ISRO has given us this data. Thrust requirement is 1 millinewton. Please be careful. 1 millinewton only. Although it is a 10 kg, but the thrust requirement in one axis is only 1 millinewton. Very small. Why? Although it is a 10 kg. Because they are in the vacuum. As they are in the vacuum, you need a very little force to move. That's why 1 millinewton is sufficient. And we have developed, it will range is 1 micronewton to 1 millinewton. Okay. And there is a propellant. In the previous case, it was a solid phase propellant, dust powder. But in this case, I have used the H2 only, water, as a propellant. The concept is that this is a device, cross-sectional view, the top view I have shown you, where you have a chamber, which is known as a vaporizing chamber. Okay. And you have an inlet through which the fluid will come inside this chamber. And in the other side, you have a converting diverging nozzle, in plane converting diverging nozzle. Okay, so this chamber, microfluidic channel, diverging converging nozzle, all are mechanical design. I have to design it. What should be the dimension, optimum dimension. At the same time, you have, in the vaporizing chamber, you have embedded resistances. Embedded resistance. It will act as a heater. Once you fabricate, then you can cover it. This can be fabricated in a silicon, and once you, by micromachining process, once you fabricate, you just cover it. So it will be like this. And here, through inlet, water will flow. Whenever I require, from inlet, water will flow and come inside this chamber. Once it comes over here, then you can switch on your heater power. As the heater is on, the temperature of the chamber will go to the 100 degrees centigrade slowly. Okay, and immediately it will go. As it goes to the 100 degree, then the water will boil. Simply it will boil, vaporize. Once it vaporizes, where from it will come out? The vapor will come out through this nozzle. Through this nozzle it will come out, because that side it cannot go. because it is connected with the inlet tank. It cannot go. It will only move in this. As the vapor comes out, just like our rocket firing, you are getting the system will get a thrust, and that's why it will move in the other direction. This side, the water vapor coming out, thrust will go, and the satellite will move in this direction. How much requirement? Only 1 millinewton. Okay. And how much water flow? You can see, I'll show you some data that it is only the few nanoliter volume of water is sufficient to produce this thrust. Okay. So it involves the microfluidics part. Not only just a heater in the electrical, you have a mechanical. The converging diverging nozzle is a very, very important factor to get the optimum thrust value. And that also depends on what is the flow of the propellant. And it is, as it is flowing from the inlet to outlet, it will vaporize. And for the vaporization, you require a optimum amount of the heater power. That means it is in the electrical domain. So you have a mechanical, electrical, physical, chemical, all together you have to work for the design. More of this micro heater design, electrothermal analysis, it is there. I just quickly go through this. This is all about the very basic concept, how the heater will be designed, how much heat is required. For that, different convection and conduction heat flow is there, thermal energy flow is there. So you have to work on that. And then from that you have to get what will be the electrical power requirement. Okay, finally it is the electrical power requirement, and based on that, what is the resistance value finally. Okay, and that resistance will be embedded on the silicon surface. So this is the all design, and here it is the probably the micro nozzle design. In the micro nozzle design, you can see how the area ratio means it is the throat area versus the outlet area. This is called the area ratio. How it will vary with the thrust coefficient versus temperature. Okay. I'm not going into the details. Some of our simulation work I'm showing now. Here you can see when it is done in the simulation, I have to see what is the pressure at the outlet. At the outlet, this is the inlet side. Inlet side, you have a huge amount of pressure. But at the outlet, it is at the atmosphere or it is at the vacuum. Therefore, it is the blue curve, it is a very less. Okay, so that way the pressure I have to check what is the pressure distribution. Then what is the fluid velocity distribution. Okay, and the Mach number. So all the mechanical design you have to perform to get a optimum value of thrust. Once you've done, then you have to do all the processing part. Using the 2FR process, you have to etch it, you have to integrate the heater, you have to make the vaporizing chamber, microfluidic channel, inlet outlet nozzle. All this can be done by the microfabrication technique. And after that, you have to bond it together. I have just shown you this slide. This is just one view, one side view where you have a micro channel here. I hope you can easily see these images. Here you have a vaporizing chamber, and this side you have a inlet outlet channel, inlet outlet nozzle. The diverging converging nozzle, and which is in plane nozzle, in plane. Okay. And this is after your fabrication, and then you have to connect it. For the electrical connection, the resistance you cannot see because it is integrated, but you can see the electrical wires are connected to give the power, electrical power, and to give the water in the inlet. This is the through pipe. Okay, and vapor will come. This side you have an inlet, and other side you have a nozzle. Here the vapor will come out. This is the whole concept. And that we have some thrust value we have measured. Just suppose what is the heater power requirement? The thrust value, it is going to 1000 micronewton. That means 1 millinewton, because this is our specification. 1 millinewton I have to achieve. So to get the 1 millinewton thrust, you have to give a power, heater power of 3.4 watt. and that you can achieve with the area. I mean, the converging diverging nozzle is this, and this is the flow rate. Water flow rate is 2 milligram per second. Okay, so it is quite feasible, and we have achieved all this data, and we have measured thrust value for the different, different thorough characterization we did, and the specific impulse we also achieved the same value. Now, at the end, just I'll show you. I do not know whether you can see it or not, but I'll go to the. Is it visible now in the slide? Is it visible?
Yes, sir. It is.
So here, this is your. It is the inlet flow, inlet tube. You can see the sensor actuator. You can see, and top of that, just for visualization, I have put a slide. I have put a very thin copper foil, and as you can see, there is a water flow is there, and water is flowing, and vapor comes out. The copper foil will now move. Okay, this is just for the demonstration purpose to you all, and here I can see we did it in the atmospheric pressure, but actually it will be in the vacuum, where the pressure is very low, and so it can easily move the 100 kg, 10 kg. Okay, this is all about. Okay, and thank you all for your patience. So I'll complete it here. Thank you.
Thank you so much, sir. Thank you very much for such an informative session. Now the session is open for questions. So audience, you can ask questions and get it clarified with Professor. Any questions from the participants?
It is there is no questions.
Okay, sir, I have one question.
Yes.
So in the micro accelerometer, so you made 4 cantilever flexures to form a Wheatstone bridge.
Yeah.
Yes, sir. So you showed 2 flexures in the same side of that proof mass, and other 2 will be at the same side. So why can't we have different flexures on all 4 directions?
Because it is about the how the mechanically you will get the rigidity, bring the rigidity in the x and y plane. If you put at the each cantilever in one side,
okay,
then you will not get that much rigidity in one axis. Instead, if you put the 2 cantilevers in one axis, then it will be much more rigid in this direction. Other direction, it will be less. So it is a combination, and bring it to the optimum design, by which ultimately you will get a very low off-axis sensitivity. Okay, people have done it. We did with this design. Okay. Yeah.
Okay, sir. Okay.
So if there is no question, so thank you all.
Okay, sir. Thank you so much, sir.
Okay.
It was really an interesting lecture. Thank you, sir.
Thank you. Thank you, Afzal.
Thank you so much, sir, for your kind presence and accepting our invitation.
Thank you.
Okay, sir.
Bye. Bye, all.
Thank you, sir.
और हो गया साले।